It somewhat evolved from the talk I gave as a keynote at FMCAD a few years ago. So, I hope you will find it interesting and relevant. Now, so this is a serious title, but so just, to prepare you for the rest of the talk, which will not contain a single formula. So the actual title is Why Do Things Go Right or Wrong in Our Life? Or, where researchers who don't really have life outside of academia, right? So, and also what do I know about life? So in computerized systems. So why do things go right or wrong in computerized systems? So the motivation is the modern computerized systems are huge and difficult to understand, as we all know. The code that sent Apollo to the moon in the 1960s was just 40K lines of code. But nowadays, so Facebook code base is about 62 million lines of code. And actually, I checked this number a few years ago. It might be even bigger now. Modern cars are running hundreds of millions of lines of code. And the Google code base, according to last count, is about 2 billion lines of code, which makes it, for all intents and purposes, a black box. So this is very challenging in itself. And so I think that Facebook are not doing them anymore, but they used to do this testing and verifications symposia annually. And if you attended one of them, you would have heard them talking about how they test and verify their systems, and this is essentially mostly black box because nobody can possibly do white box verification or testing of such a huge code base. So even though the systems are, for all intents and purposes, black box, we still should be able to answer the same questions we were supposed to answer when they were smaller and we were able to verify them white box, which are specifically, can we understand and fix errors? Can we be sure that the system is correct? And essentially, what does the system do at all? So I guess the last question was not really relevant when systems were just 40K lines of code, but it becomes more and more relevant as system grows and there is no single person who understands the whole system from the beginning to an end. And also those multi-million lines of code systems, or even billion lines of code bases, they take a long time to develop. So in fact, the original developers might not be there at all anymore. So it's a very valid and very important question. What does the system do? Now, if this wasn't complicated enough, now we have a new generation of systems, which is all kinds of neural networks, which are black box by design. So even looking inside and having access to these layers and the neural interaction is not going to help us at all to figure out the logic and the way of reasoning of these neural networks, even though we still have to answer these three questions for neural networks as well. So this is so we have a problem, right? We have to answer the questions. It's not clear how we do it. So I'm going to claim that the actual causality, which was introduced by Halpern and Pearl, so Joe Halpern and Jude Pearl, Joe Halpern sadly passed away recently, a couple of months ago. So they had a seminal couple of papers, a set of two papers in 2001 that introduced actual causality and actual causality framework. Since then, it was developed by Joe Halpern further with many papers refining the definitions. And essentially, it's a theoretical concept from AI. So in 2001, when it was introduced, it was still considered as very esoteric and not relevant to the real world, kind of philosophical, right, on the border of philosophy and AI. It extends causal counterfactual reasoning, and I think this is pretty much what I'm going to say about it. One of the breakthroughs that made it useful for practical applications was actually the quantification of actual causality that was first introduced by Joe Halpern with me in 2004, I think actually 2003. I need to fix this. And it allowed us to rank causes by importance. So which causes were more important for the output and which were less important. And this turns out to be very useful. These concepts in general, they turn out to be very useful. As all good things in life, all good things in life are either intractable or undecidable. Those are intractable, decidable but intractable. But it doesn't stop us from using it because there are efficient approximation algorithms and sufficient partial solutions. So just to separate different causality types. So when I was talking about causality, even I think 10 years ago, I didn't need to explain that, but recently causality became very fashionable. But the type that is more fashionable is a priori causality, otherwise known as type causality. So what is type causality? Is using causal reasoning to predict outcomes in the future. So we look at the population, and based on the population, we predict what's going to happen in the future. So for example, this doctor has her practice in a very pollution heavy area, and she's awaiting her next patient, and she's saying this is terrible pollution, so my next patient is likely to suffer from breathing problems, because this is based on the what she knows a priori and what she's seen so far. This is the situation with most of the patients. Now, actual causality deals with the things that already happened. It analyzes events that already occurred. Okay, so already occurred. So the next patient walks in, and actually he broke his leg. Yeah. So this is actual causality. Now we're going to analyze the causes for breaking his leg rather than the pollution. Which is actually suspiciously timely given that I broke my shoulder. Okay. So anyway, so this is that. So my area of expertise is actual causality, is analyzing the situations that happens already and finding and ranking causes for the outcome, which helps us then to fix the problems, of course, to understand and to fix the problems. Okay, so I'm not going to talk about causality anymore. If you are interested, there is quite a bunch of talks. I think they're available online where I describe it further. And of course, even better than that, you can look to one of the multiple Joe Halpern's talks where he explains it way better than I ever could. But let's go back to the motivation. So we have, just to remind you, we have these questions. Can we understand and fix errors? Can we be sure it is correct? And what does the system do? Now, the two questions on the left are actually verification, right? So can we understand and fix errors, and can we be sure the system is correct? These are proper verification questions. Whereas the first one is debugging, and the second one is giving a stamp of correctness, right? Correctness stamp, which is what formal verification can do as opposed to more static analysis and testing techniques. So we're going to talk about debugging. I'm not going to talk about the correctness stamp, even though it is also relevant, just simply because I don't have time. The part on the right, what does the system do? It is explainability. So explain how the system arrives to this conclusion. And I'm going to talk briefly about this as well, especially since this is currently my main work lies in this area of explainability. Okay, so we're starting with the debugging. So in formal verification, right, we all know the roughly the structure. So we have a huge and difficult to understand system M, presented as a state transition graph, as a symbolic system, as whatever, right, in whatever formal way you like. And we have a correctness specification. So here it is a temporal logic formula. It can be a finite automaton. It can be presented in some other formal way. We feed them into a model checker, which for this purpose it's a black box, right? It says runs some bunch of complex algorithms, and then it either outputs yes or it outputs no. So yes means the system is correct, versus some sanity checks, which again I'm going to ignore for now, but they definitely I have some thoughts about that as well. But let's focus on the no. So if the answer is no, then it gives a counterexample. Now, a counterexample should be used to understand and fix the problem. Okay, the question is, do we understand the counterexample? And can we actually use it to fix the system? So these look like very silly questions, but in fact, the question of how do we show the user what went wrong is a very important question. And in fact, so I worked before joining King's in 2013. I worked for 8 years at IBM research in this formal verification department. And I saw firsthand what happens when we have a counterexample. So that was, right, IBM has its own tool for verifying hardware. And the counterexamples look much worse than that, right? So this is an example of a very simple timing diagram. Basically, counterexamples, you have waves of signals, they are right as zeros or ones. So you have thousands of signals and thousands of clock cycles. And honestly, nobody can ever figure out what went wrong with the counterexample. Like I promise you, nobody ever used the counterexample to figure out what went wrong and to fix the system. What people did was trying to rerun the verification with a simpler property or with another property. Okay, so this is obviously a miss, right? We cannot use the counterexample. So using actual causality, we were able to augment this tool, the formal verification tool, or specifically the counterexample presentation, with um, marks for causes of failure. And now, since specifications are usually very simple, so this is an example of a very simple specification. It is simple. It is written in temporal logic, but it is simple. It says merely says that the next transaction doesn't start until the previous transaction ended and outputted status valid, and then the system is in its ready state, right? Um, the number of causes is actually very small. So we're able to mark the causes, which are the cycles and values of variables, on the timing diagrams as red dots. And this was actually really helpful. So it worked, it was really useful. We know that it's useful because when it was not upgraded with version upgrade one day, we got lots of phone calls, right? It was before 2013 from the user saying, where are my red dots? I need my red dots to understand the counterexample. So this is really useful um, aid for debugging. Now, following this work, and when I'm saying following, it's following not just chronologically, so that was 2009. And in fact, there was a lot of discussion. I think that it was first presented at CUP. There was a lot of discussion of what is this causality thingy. So many applications of causality and responsibility to software engineering. There is a CREST workshop, which was collocated with ETAPS for a long time. It is now collocated with CAV, and it's going to run JSON in Flock this year. And also there is ongoing work of causal debugging for software. So causal debugging for software is more complicated because obviously we don't have this nice structure of Boolean variables and the clock cycles. And in fact, the state of the art for software is still statistical analysis of fault localization. So statistical analysis for fault localization, I'm sure you all, came across it in your debugging effort. It looks for correlation, basically. So elements that appear more in failing traces than in passing ones are suspicious. And then elements are ordered by the degree of suspiciousness. Again, correlation based. There are many formulas, they're all based on correlation. And then they're presented to the debugger, to the user debugging the system, to look at them one by one and to figure out which was the cause for fault. Of course, correlations work wonderfully well. So this is an example of yearly total gross income of US farms versus Google searches for who is the doctor. See, the correlations are amazing. And this is another example of a number of Grand Slam finals played by Roger Federer, where I guess before he retired, right, until 2015, versus the number of electronic engineers in New Mexico. Again, wonderfully correlated. Yes, of course, I'm kidding. So the link for this is on the bottom. So correlations are not great, right? So we need to actually use actual causality for that to understand the causes better rather than correlations. So this is ongoing work. I'm going to very briefly mention it at the end. Okay, so in general, I claim that verification is a great application for causality. So why is that? So first of all, interventions are always possible. So the way actual causality works, the analysis actually works, is that we introduce interventions on the values of the variables and observe the outcome. Now, interventions are in software and in hardware are always possible, unlike other domains, right? I mean, just it amounts to change in the value of a variable on a line of code. And compare it with the situation in healthcare, right? So as opposed to software where you can say, well, instead of x equal to y, let's say what happens when x equal to once, right? So just a mutation. Whereas in healthcare, okay, imagine a doctor that is trying to figure out what is the cause for the patient's poor outcome or, a poor well-being. And they say, well, okay, now let's replace you with the same person, but without peanut allergy. Okay, that really doesn't work, right? So interventions are always possible. Now, it's usually clear what the variables are and easy to calculate the equations. Now, main challenge in all these applications of causality, one of the main challenges, is constructing the correct causal model. And in fact, this is a subject of a lot of debates in philosophy about the causal model and what actually is a causal model. And in fact, constructing the right model that captures the essence of what happens is half of the answer. And it is challenging in many domains, including healthcare, for example, but fortunately not in verification, right? We have a system, we have its environment, it's usually pretty clear what the model is. The system are deterministic and all deterministical variables are known. And there is no noise, no hidden confounders, which are some factors that affect the system from outside. With concurrent systems, there is some randomness, but again, all this can be modeled and it's still better than in other domains. And the approach is agnostic to the model checking algorithm. In general, it's agnostic to the algorithm that outputs the results, which is very nice, right? Because the verification algorithms, they advance very fast. And it's nice to have a method that is completely agnostic to the actual nitty-gritty algorithms that give us the answer. Okay, so going back to this motivation slide. So we talked about debugging, and the causal models is obvious or easy to construct. In contrast, in explainability, actually the causal model is a black box. So let me show you what I mean. So we, in my group, which is like we developed the main framework, which is called REX, and I'll spare you the wondering what it stands for. It's causal responsibility-based explanations. Of course, it's also a very nice dinosaur. So it's reasoning about decisions made by black box software. So, for example, neural networks in our case, but it can be any large software that you treat as a black box. So, in order to reason about these decisions, we should be able to intervene on inputs, which is the input transformation here on the slide, and we should be able to observe the output. So basically, we're given this black box to play with, but we cannot open it. But we view this black box as an unknown causal model. And even though it's unknown, we can deduce many things by playing with inputs and observing the outputs. Many things that are actually rooted in actual causality theory and have solid and provide solid guarantees. Right, so this is our black box causal model. So the high-level structure of REX, it was first built for images. This is why the example is from image. So we have an image of a red panda, for example, and we have its label, which is red panda, which is what the black box gave it. So it's image and its label. And then REX, our tool outputs a minimal subset of the input that is sufficient to get the same label. So in this case, we have, for example, so we have this panda's face, which is sufficient for the neural network to give it the same label. So this is also going to be labeled as red panda, and it's a minimal such subset. So any smaller subset of the input is not going to be labeled by red panda. And it is a modular, so it has what it does essentially, it ranks parts of the input, in this case pixel, by their effect on the output. So it kind of approximates causal responsibility. And then it extracts approximate explanation by using greedy approach. But essentially it's very modular, so you can use another algorithm in the first part or another algorithm in the second part. Okay, so this is an example of the output. So we had here an image and it's labeled ladybug, and then it outputs, the first part outputs this kind of landscape of which is also called, if you've seen silency landscape. So this is what it is. It's similar, which is the importance of different pixels for the output, and an explanation. So all these grayed out parts, they are not important. So the part that is sufficient and minimal for the label is this small area with the part of the ladybug wings, right? This red one with dots. Okay, so here's an example of what we found. So we found quite a lot of interesting things. Here is an example of subtle misclassification. By the way, all the examples are taken from standard benchmarks, usually ImageNet for images. And the networks are standard, right? So this is, they're all like really valuable. So this was labeled as cowboy hat, which actually seems okay because it's a child wearing a cowboy hat. But when we ran our explainability tool Rex on it, it said because of this part, and the part is child's face. Now, clearly, this is misclassification, right? So the model sees a child face and it outputs a cowboy hat. Now, this not only it provides misclassification, but it also provides us with some insight about what actually caused the misclassification, right? We can guess now what happened. So we can use this information to retrain the model to remove these errors. So this is kind of one of the uses of explanation. And this, in fact, we have now an ongoing large scale project where we have a neural network and it has some training sets. So it is trained. And then we have a set of inputs and their labels. And then we run a Rex, our tool, so to extract a set of explanations. And then we're going to feed them into analysis of filtering. So this is the part that we are still thinking about, right? This is why it is ongoing work. And based on the analysis and filtering, we're going to extract a fine-tuning set that is going to improve the quality and improve correctness of the model answers. So explanations are useful. And just to, so I see that the time advances, so just to say, it's not a lonely dinosaur, right? We not only have explanations for images, so this was the first version, and it provides one explanation for an input that is an image. But actually, we have quite a lot of other versions. So we have MREX or multi-rex, which provides multiple explanations because this sufficient set, this minimal sufficiency doesn't have to be a single one, right? There might be multiple, and so this is our MREX with multiple explanations. We have a frequency rec, which looks at frequencies and provides explanations for audio. And this is, in fact, it's a branching out of the SpecRex, which is for spectra, for medical spectra, and it is Raman spectroscopy. This is a very well-known technique for analyzing cells for cancer. In general, a lot of our work is in the healthcare domain, simply because we are funded mainly by Child Hub, which is Causality in Healthcare AI Hub, big PSRC funded project. Now moving forward, so there is a 3D Rex which provides explanations for 3D objects. We also have video Rex, which I didn't put here, but essentially you can view video as also kind of 3D object, right? There is a NITO, it provides explanations of absence, which is very interesting. And unfortunately, I don't have time to talk about the algorithm. It's actually not based on Rex. It's a different one, but still it provides minimal subsets of the inputs that are sufficient to get the same output of absence, right? So for example, in the medical domain, it's like, why is there no tumor in this brain scan? We have Black Cat, which is for adversarial attack, which uses this explanation to construct imperceptible and explainable adversarial attacks. So some of them are done, right? Those are done. So those with these are done. Now we have several under construction, which we have a version for tabular data, which is under construction. And we have software X. So I promised I'll mention it again. So this is to improve fault localization using causality. So this is SoftRex for software. And in future work, we're going to look at multimodal, which again is very important in healthcare, where we have patients' data and the results of labs and tests and imaging data as well. And of course, LLM-Rex, which becomes more and more important now that there are, you probably have seen, right, the recent papers and discussions. The first they talked about, well, we cannot figure out how the LLM outputs its text, it gives its output. So then let's maybe extract a chain of thought, but then actually chain of thought is not always how it reasoned and how it arrived to the answer. And now there is a paper, the recent one, which is now we have a fragile opportunity to intervene in the chain of thought and understand how it works. So definitely LLM Rex is our next big project. And I think that's all. And I should be right on time for questions.
Thank you so much, Hana. Any questions for Hana? Anyone? Is that okay? Yes.
Thank you, Hannah, for the interesting talk. I was interested in the statement that you made about that this kind of model agnostic, so you can this black box that you use could be swapped around. So for the image examples that you gave, if you were to, for example, use like a vision transformer, so kind of a bigger model, how does this technique kind of scale? Like, does it still work?
Okay, so I guess there are two separate questions, right? One is, does it work? And the second one is, does it scale?
Yeah.
Right? So first of all, yes, it works because we really, truly never opened the black box. So right? So it's exactly like this. We only need access to it to run it and to see the outputs. Does it scale? So as all black box tools, it requires quite a lot of calls to the model. So it scales as well as the model scales, right? So if the model is very slow, which again we encountered with some models that work in the health scale domain, then it's going to be really slow. But it will work, right? So
Okay, thank you.
Yep. Welcome.
Any other questions? In that case, I'll ask one final question, Hannah, before we let you go and rest. You mentioned that your next project is for LLMs.
Yes.
So how much of what you've done transfers? What do you expect the challenges to be? Because obviously that's where the gold is at the moment. So what is the big jump?
Absolutely. So the big jump is that instead of classification, so there's one label, right? So you give it an image, it says panda. Right now we have a long text with the prompt, and it's not quite clear. So first of all, it's not clear how to modify the prompts, the input, because as opposed to, for example, images, when we can cover parts of it, or we can introduce blur or different colors. With text, if you remove the word not, then the meaning completely switches, for example. But also, it's not the effect on the output is less clear. So if the output is different, how different is still equivalent or close by, right? So all these complications, they make the algorithms much less clear. But we're working on it.
Lovely. Thank you so much.
Definitely where the challenge is.
Thanks again. That clarifies things. And thank you again for agreeing to do this. And we wish you a speedy recovery and hope you get well soon. Thank you.
Thank you.